Hello and welcome to another online lecture for General Physics 2. This one deals with the topics of magnetism and magnetic fields. It also contains probably more conceptual multiple choice questions than any of the previous lectures, and so if those are helpful to your learning, I would encourage you to go through them with me. When we read the question, you can then pause the video and see what your answer is predicted to be before I talk about what my answer is. If, however, you find there's too many questions or those aren't really helpful to your learning, then I would encourage you to use the Panopto features and scroll through the slides until you get to the slides that actually talk about the relationships between moving charge and a magnetic field and the force on that moving charge. So here's the first of many concept questions. If we take a bar magnet and have a steel ball that's hanging from a thread or a string and observe that the steel ball is attracted toward the bar magnet. If we flip the bar magnet around and the south pole is brought near the steel ball, the ball will be what? Attracted to the magnet, repelled from the magnet, unaffected by the magnet. It will be attracted to the magnet. Steel is not a magnet itself unless you've done something to magnetize it, but it is attracted to the north end of a magnet. However, it's also attracted to the south end of a magnet. The paper clips that we were using in the lab were made of steel, and the same principle applied there. The paper clips were attracted to either end of the bar magnets we were experimenting with. How about a compass? A compass, as we observed in the lab, swings and aligns so that one of the needles points toward the geographic North Pole. What does that tell you about what a compass is? A compass itself is a magnet, an object attracted to magnets but not itself magnetic, an object attracted to charged objects but not itself charged, or none of the above. The correct answer that you should have deduced in the tutorial is that a compass itself is a magnet. At first it seems to many that it's an object attracted to magnets but not itself magnetic. However, if you bring a bar magnet near a compass and observe that one end of the bar magnet attracts to one of the needle ends on the compass, if you flip the bar magnet around, the compass needle will flip around as well, telling you that the end that was previously nearest to the bar magnet is now repelled, the opposite end of the compass needle is attracted, and attraction and repulsion are characteristics of things that we classify as magnets. A compass needle that the end of the compass needle rather that we call north points toward the geographic North Pole. And what does this tell us about the geographic North Pole of the Earth? There must be a magnetic North Pole, a magnetic South Pole, a negatively charged pole, or a positively charged pole. The correct answer is that there must be a magnetic South Pole at the geographic North Pole of the Earth. Again, by definition, since we're calling the end of the magnet that points to geographic north the north end of that compass magnet, then we've also observed that opposite poles of magnets attract to one another. So the pole that is in the geographic north region of the Earth must itself be a magnetic south pole. It's not either positively or negatively charged. We saw in tutorial as well that when you bring a bar magnet near a pith ball, which is attracted to charged objects, the pith ball was not attracted to the magnet, and this indicates to us that there's not net charge buildup at the poles of any sort of magnetic material, including a bar magnet or the Earth, which is acting like a giant magnet. So here's a little map actually for, I don't know, I guess trivia points here or something, but this is actually the locations of the actual magnetic pole and the magnetic south pole in this case at or near the North Pole of the Earth. So first of all, we note that it's actually not right at the geographic North Pole, which is up here in the peak of this cone, but the magnetic North Pole or magnetic South Pole rather, has been wandering north over time, and so these data points have actually been observed. the earlier data points stretching back to the 1600s have been modeled based on other things that you can look at in nature. So the magnetic pole itself is not steady in location, and in fact, scientists who study seafloor spreading at the bottom of the Atlantic Ocean have noticed that periodically over Earth's history, the magnetic field of the Earth seems to have reversed directions every few 100,000 years. So even though currently our North Pole, geographic North Pole that is, contains a magnetic South Pole, at some point, if Earth lasts that long, it's speculated that it will once again switch and it will become a magnetic North Pole. Of course, we can then rename it to be south, I suppose, if we want to keep the convention about our compass needles to be the same as it is today. So Earth is modeled, in fact, yes, as a giant magnet. The south pole of the magnet doesn't line up directly at the north geographic pole, but unless you're doing orienteering near the North Pole or near the South Pole, the compass needle that we use points north enough that we can use it to ascertain what direction actually is north, as long as we have a rough idea, 50-50, which general direction is north. Okay, what about bar magnets? Two identical bar magnets are placed rigidly and anti-parallel to each other as shown. At what locations, if any, is the net magnetic field close to zero? The points we've labeled A only, the points we've labeled B only, the point we've labeled C only, the points we've labeled D only, or some combination of those. The correct answer is at point C only, which is option 3. Recall that when you were using compasses near bar magnets, near the north pole of a bar magnet, the magnetic field points directly away. You'll have a slight pull from the south pole of this other bar magnet down here, but those will not cancel each other out in magnitude or direction, so it won't be zero at any of the points labeled D. At B, the magnetic field points away from a north pole and toward a south pole, so the direction of the magnetic field from each of the bar magnets is actually in the downward direction here at point B. But at C, at the midpoint between the bar magnets, since we've observed that magnetic fields go out of the north end but then curl around the magnet and come back into the south end, the magnetic field from the top bar magnet at point C would be pointing to the right. The magnetic field from the bottom bar magnet at point C would be pointing to the left. Since point C is the same distance from those two bar magnets and you're told the bar magnets are identical, that's a point where those field vectors would cancel out and we would get no magnetic field. This and the exercise and tutorial, of course, demonstrate that we can use this principle of superposition in ascertaining magnetic fields as well. In other words, if we know what the magnetic field looks like from one magnetic object and we know what it looks like from the other object, we can add those two effects together to find the net magnetic field if the situation warrants that. In what ways does electricity and magnetism differ? And the options are: electric field lines always point from positive to negative. Magnetic field lines point from north to south outside the magnet and south to north inside. Conducting shells shield electric fields while they do not shield magnetic fields. Opposite electric charges attract while opposite magnetic poles repel. And magnets always have two poles. Single charged objects can be either positive or negative rather. The correct answer to this is that 3 of those 4 statements are correct. Number 1 is correct. Electric field lines, by convention, always point from positive charges to negative charges. So in fact, they can be thought of as starting at positively charged objects and ending at negatively charged objects. But what we saw, or at least tried to model in the tutorial, was that inside a bar magnet, the magnetic field lines point from south to north, while outside the bar magnet they point from north to south. And so one key difference is that magnetic field lines are actually continuous. There's no ending and beginning place for a magnetic field line, but outside the magnet it goes from north to south, inside from south to north. Conducting shells shield electric fields. We saw that a little bit in our electrostatics work, and again, a conducting shell has the same value of electric potential everywhere, so without a changing electric potential there is no electric field. But they don't shield magnetic fields, and if you put a paper clip inside the cup like we did in tutorial that contains aluminum foil around the paper clip, you will still get a magnetic interaction where the paper clip will be attracted to the magnet. However, number 3 is not true. We've said before that opposite electric charges attract, and our observations of magnets lead us to believe that opposite poles also attract, and like poles repel. 4 is correct, though. Magnets always have 2 poles. If you take a bar magnet and break it in half, each half now has a north and south pole. Continue to break that in half, each new half or quarter has a north and south pole. And you can continue this down, at least theoretically, to the single atom level. And we'll talk a bit later about a model for what makes things magnetic in terms of the properties of the atom. Alright, so some questions about the exercise you completed in lab involving these E over M apparatus. When you pointed your magnet perpendicularly to the electron beam, so this is supposed to be a bar magnet held at the side of the apparatus, the beam, was it deflected horizontally, that is, in the plane in which the magnetic field is lying? Was it deflected vertically, or was it not deflected at all? Hopefully, everyone was able to observe that it was in fact deflected vertically. So the direction of the magnetic field and the direction of the beam can be thought of as forming a horizontal plane. The beam itself, however, was deflected out of that plane in the vertical direction, either up or down, depending on how the magnet was held. I don't know if you tried this in the lab, and if not, you might not have the answer to this, but if you pointed your magnet parallel to the electron beam, what would happen to the beam? Was the beam deflected vertically, deflected horizontally, or not deflected at all? And it turns out if you do this, you get no deflection, so please excuse the nice circle shown here. That's actually what the beam, of course, looks like when we turn on the coils. But if you just have the straight line electron beam and you line your magnet up with it, we actually observe no deflection. It can be, of course, tricky to line up the direction of the magnetic field from the bar magnet in the exact same direction as the electron beam, but when you do that, there is no net deflection of the electron beam. So we're going to use those to put together a rule for describing what we observe happening to moving charged particles when we place them in magnetic fields. But we need an idea from Physics 1 to build that idea, and so here's a bit of review. If I have an object, and that's the blue square in my picture, that is moving to the left, so here's my velocity vector for that object. If I have a force that acts on the object in the same direction the object is already moving in, what happens to the object? Is it going to speed up, slow down, change direction, or do some combination of those? Speed up and change direction, slow down and change direction, or keep moving at constant velocity? The correct answer is that it speeds up only. When you apply a force in the direction something is already moving, that produces an acceleration in that direction, so that increases the velocity, but it increases only the magnitude of the velocity. The direction of the velocity stays exactly the same. How about this one? If an object is moving and now you apply a force that's a 120-degree angle to the direction that the object is already moving, is the object going to speed up, slow down, change direction, or some combination of those? And the correct answer here is that number 5, it will slow down and change direction. One way you can think about this is if I have a force at this direction, that force could be broken into a horizontal component and a vertical component. Well, the vertical component of the force will be exactly opposite to the direction of the motion, so that part of the force will act to slow the object down. But there's a component of the force as well that is perpendicular to the direction of motion. And recall from Physics 1, you learned and hopefully observed that when objects experience forces that are perpendicular to the direction of their motion, what that does is it changes the direction of the velocity vector. It doesn't change the magnitude, so the object will keep moving the same speed, but it changes the direction of motion. In this case, since you've got both those components, it'll change the direction and the speed, and so number 5 is the correct response here. So let's try to summarize what we observe in terms of the motion of charged particles in electric fields and magnetic fields. When we place a charge in an electric field, it always experiences an electric force, whether the charge was initially moving or whether the charge was at rest when we placed it there. However, that's not true about charges in magnetic fields. When a charge is placed in a magnetic field, it doesn't automatically experience an attraction. If it did, we would see, for example, a pith ball, which contains millions and millions of charges, being attracted to the magnetic field created by our bar magnet. But when the charge is doing certain things, and chiefly among them is moving, in a magnetic field, under certain conditions it experiences a magnetic force. So some things that we observe from the lab, the charge has to be moving. We needed that electron beam in the E over M apparatus in order to deflect that beam with the magnetic fields that we put near that electron beam. Also, it turns out that the velocity of the moving charge has to have at least a component, if not the entire vector, perpendicular to the direction of the magnetic field. So if you brought the magnet in from the side of the electron beam, you observed a deflection vertically. If you brought in the magnetic field vertically relative to the beam, you observed a horizontal deflection of the beam. But if you brought in the magnetic field parallel to the beam, if you tried it, you should observe no deflection. So we need at least a component of the moving charge's velocity to be perpendicular to the direction of the magnetic field. So here's a picture I grabbed from an old textbook, but it illustrates what a moving charge does in an electric field and what it does in a magnetic field. So if you have a moving charge and it enters a region of a magnetic field, say in between the plates of a charged capacitor, that charge will feel a force in the direction of the electric field, and that will result in a curve to the trajectory of the particle. Just like, by the way, a mass that's thrown horizontally across the room experiences a force in the direction of Earth's gravitational field and is pulled down toward the floor, making a parabolic trajectory. However, if you take that same moving charge and you fire it into a magnetic field, say the region between the north and the south pole of either two bar magnets or in a horseshoe magnet, what we end up observing is that the velocity changes direction, and that's consistent with a force being applied perpendicular to the direction of the velocity. What's more, we see a circular trajectory if the magnetic field is large enough, and that tells us that at each point the force on that moving charge from the magnetic field is always perpendicular to the direction of the velocity. If that weren't true, you wouldn't get a nice circular path. You'd get a parabolic path if the force, for example, always pointed in the same direction. So the force on a moving charge is given by this mathematical relationship, and this is written in the vector cross product form. We'll talk briefly about what that means and also show how we generally see it in an algebra-based course. So force is a vector, and we've learned about forces in Physics 1 and thought about them occasionally in Physics 2 as well. The force that a moving charge feels depends on a few things. It depends on how much charge you have, and it turns out to depend on what sign of charge you have. We couldn't see this directly in lab because we had an electron beam and there was no way to change the charge on that electron beam, but it turns out the charge matters. How fast those particles are moving matters, so that's the v, the velocity, and the magnetic field matters as well, and that's abbreviated with the capital B. The velocity and the magnetic field are both vectors, and when you need to multiply two vectors together, there are two ways to do that. You can do it with a vector dot product, and we do that when we're calculating, for example, work. Work is a scalar, but you get it from two vectors. Well, you can also do a vector what's called a vector cross product, and we also get that from two vectors, but it yields another vector quantity, and one of the hallmarks of a vector cross product is the vector that is yielded is in a direction that's perpendicular to both of the vectors that went into that vector cross product. We generally end up writing it like this. The force is equal to the magnitude of the charge, so we ignore the sign of the charge in this convention and we use other rules to figure out what direction the force has to be in, times the magnitude of the velocity, times the magnitude of the magnetic field, times the sine of theta. And theta, like it is in many of these physics relationships, is the angle between the two things in this calculation that are vectors, namely the velocity and the magnetic field. So when the velocity and the magnetic field are perpendicular to one another, the angle between them is 90, the sine of 90 is 1, and we observe the maximum amount of force. If the velocity and the magnetic field happen to be in the same direction as each other or 180 degrees different, the sine of 0 or the sine of 180 degrees is 0, and so we get no force in those situations. And obviously if the angle is somewhere in between there, we get intermediate amounts of force. So if you are familiar with how to do vector cross products and have used that in the past, feel free to use that way. One of the nice things about doing a vector cross product is the magnitude and the direction fall out of your calculations. Most of us, however, have not formally seen a vector cross product, and so we will stick with this mechanism for calculating forces and use a right-hand rule to figure out what the direction of the force is. The magnitude of the magnetic field is found by rearranging these. So if you have some way of figuring out how big a force a charged particle feels in a magnetic field, you can, and you know that charged particle and how fast it's moving, you can figure out how strong the magnetic field is from something. And the unit for magnetic field is named in honor of Nikola Tesla, who I'm guessing many of you have heard from, a rather eccentric but brilliant scientist. And it's capitalized capital T. So the magnetic field itself is written with a capital B. Units of the magnetic field are the Tesla, and that's capital T. A 1 Tesla magnetic field is a rather strong magnetic field. 1 Tesla, by this definition here, must equal 1 Newton, that's the force unit, over 1 Coulomb, that's the charge unit, and then the velocity would be in meters over seconds. So a Tesla is a Newton second per Coulomb meter, for those of you keeping score at home with units. So if we only use that relationship to figure out the magnitude of the force, then, by the way, that's called the Lorentz force in many places that you would read about it. We need another rule for figuring out what the direction that force is in, and so what we end up using is something called a right-hand rule. The magnetic force points in a direction that's perpendicular to both the magnetic field and the velocity of the particle, and so we have this right-hand rule for figuring out what that direction is in. So what you do is you point the fingers of your right hand in the direction of the velocity that the charged particle is moving in. You curl those fingers toward the direction of the magnetic field, and your thumb is then pointing in the direction of the force that's experienced. So if the particle was moving due right, you'd point your fingers due right to line up with the motion of the charged particle. You curl them into the direction of the magnetic field. Your thumb rather, is left pointing up out of the plane, and that would be the direction of the force on that charged particle. Other books have slight variations on that. Some places say you point, like your index finger in the direction of the velocity. You point your middle finger in the direction of the magnetic field, and then your thumb is left pointing in the force direction. So this one is obviously one approach. I would encourage you to also read in the textbook and or Google magnetic force right-hand rule and see which way that somebody talks about it makes the most sense to you. If the charge is negative, the force is actually opposite to the direction predicted by the right-hand rule, because this change in sign of Q changes the direction of F. And so there are two ways you can approach this. My preferred way is to always use the right-hand rule, and then one of my last checks is to say, is this particle positive or negative? And if it's negative, simply reverse the direction of the predicted force. However, if you prefer, or it makes more sense to do it this way, you can do a right-hand rule for positive charges and a left-hand rule for negative charges, and you'll get the right answer that way as well. So here's a little bit of practice in applying the right-hand rule, and this involves manipulating your hand. So again, I would encourage you, as you're watching this presentation, to try to twist your hand around and see if you can make sense of what's going on in terms of the directions. So here I've shown a magnetic field that's into the paper. We're moving into the realm of vectors in 3 dimensions. So if you've not previously learned this, a vector drawn that's in the direction of into the paper is drawn as an X, and a vector that is coming out of the page is drawn as a little dot, or more often a little dot surrounded by a little circle. I am only speculating that this is supposed to look like the feathers on the tail of the arrow, and the other is supposed to look like the tip of the arrow coming towards you. Anyhow, if we have a positive charge that's moving to the right in a magnetic field that's into the paper, we would orient our fingers of our right hand along the direction of the velocity vector shown there in the diagram, curl those fingers into the page, since we're told that that's the direction the magnetic field points, and that leaves our thumb pointing toward the top of the screen, so the force on this charged particle would be directly up in this particular situation. You can also deduce what the charge of the particle is from looking at the trajectories of particles and sort of reversing the right-hand rule. So particle 1 here, because particle 1 curved in the upward direction, that's consistent with a force that at least initially was in the upward direction. That's the same as we just talked about over here. So if the magnetic force is in the upward direction and the velocity was due right, at least initially, that's telling us that number 1 is a positively charged particle. If I have another particle that continues through a magnetic field and experiences no deflection, even though the direction of the velocity is perpendicular to the direction of the magnetic field, that's evidence that there is no net charge on that particle. And if I see a charge that experiences a force that is opposite to the direction that the right-hand rule would predict as being the direction of the force on a positive charge, then the logic says that's a negative charge. So in number 3 here, for example, if I point the fingers of my right hand directly up toward the top of the screen, which is the initial direction that the particle number 3 is moving in, and then I curl those fingers into the screen, which is the direction of the magnetic field, my thumb is left pointing over to the left of the screen. And that would be the direction a positively charged particle would be pushed. Since this one shows evidence of being pushed in the opposite direction, particle number 3 must be an opposite charge, hence a negative particle. So here's some more practice scenarios. Again, I would encourage you to pause this slide and see if you can come up with the predicted direction of the force in each of these situations, but I'm going to run through them rather quickly and tell you what the answers are. So if you want to try it yourself first, here's where you would pause the lecture. Case number 1, I have a positively charged particle. It's moving toward the top of the screen, so I point the fingers of my right hand toward the top of the screen. I have to twist my right hand around to curl my fingers on that right hand to the left side of the screen, which is the direction of the magnetic field, and that leaves my thumb pointing directly at me or out of the screen, and so that would be the direction of the force on this charged particle moving in this magnetic field. Here are vectors that represent a magnetic field pointing out of the page. So I have a particle moving to the left. If I orient the fingers on my right hand toward the left of the screen and then twist my hand around so that I can curl the fingers of my right hand so that they're pointing toward me or out of the screen, my thumb is pointing in the upward direction. However, and I don't know how well this is showing up on your presentation, this is a negatively charged particle. So a positively charged particle via the right-hand rule would experience a force directly up to the top of the screen. A negatively charged particle experiences a force in the opposite direction, so it would be down. In situation number 3, the velocity of the particle is down, so I get the fingers of my right hand pointing down. The magnetic field is into the page, so I have to turn my right hand around to be able to curl the fingers on my right hand in that direction, and that leaves me a force to the right on this particular particle, and this is a positively charged particle, so that direction is correct. Here I have velocity to the left and the magnetic field is to the right, and while it's possible to point your fingers in the direction of the velocity, which is to the left, and curl them around so that they're pointing completely to the right, that leaves an ambiguous direction for your thumb because you can actually curl your hand around in any orientation. And you have to step back in some of these situations and think about what's going on here. The velocity is to the left, the magnetic field is to the right. The angle between those two vectors is 180 degrees. They're anti-parallel, and the force that you would see on a particle in this situation is actually zero. And you can calculate that using the formula we had a couple of slides back, or from observations in the lab if you happen to look at what happened when the beam was moving in a direction that was along the direction of the magnetic field. If I take this positively charged particle, it's moving down and to the right. The magnetic field is pointing out of the page, so my fingers are initially along the velocity and then they curl out of the page. That leaves a force on this positively charged particle that is down and to the left in this particular picture. Here's one where things aren't perpendicular, but I can still orient the fingers of my right hand to the right of the screen in the direction of the velocity of the charged particle, curl them toward the direction of the magnetic field, and that leaves my thumb pointing out of the page. However, this is a negatively charged particle, so the force on it is actually opposite to that direction predicted by the right-hand rule. It's into the page. And there would be a force in this situation. It's just not as strong of a force as it would be if the velocity and the magnetic field were perpendicular to one another. So now let's do a couple of sample problems. And we've observed this in the lab, or you should have with the E over M apparatus. If the velocity of the particle is perpendicular to the magnetic field, the particle will move in a circular trajectory. So if I'm in a situation where the velocity is to the right, magnetic field's into the page, I can use my right-hand rule to figure out that there's a force in the upward direction. A little while later, I'm moving in the upward direction. The magnetic field is into the page. The right-hand rule predicts a force directly to the left. Get to the top of the circle, my velocity is to the left. The magnetic field still into the paper, results in a predicted magnetic force that's straight down, and so you'll actually get a circular trajectory as long as the magnetic field is uniform, meaning it has the same strength everywhere that the particle is moving in. So let's use this observation to find the radius of an electron's orbit when it moves perpendicular to a magnetic field of 0.55 teslas with a speed of 6.27 times 10 to the 5th meters per second. So the electron could be part of the electron beam that we looked at in the lab activity, and it would be possible to calculate how strong the magnetic field was from those coils. It's also possible, if you know what the voltage is between the plates that you accelerated the electron beam between, you can calculate what the speed of the electrons should be in that beam. But we're given both of those numbers in this particular setup. So my first step in all of these problems, since I'm dealing with forces, is to draw a free body diagram. Now this is not an exciting free body diagram per se. There's only one force on this charged particle, a force on an electron from the magnetic field. Now, you might also say, hey, shouldn't there be a gravitational force? The answer to that question is yes, but it turns out if you calculate how large that gravitational force would be, after all, an electron has a mass of 10 to the minus 31 kilograms, so that means the gravitational force on it is of the order of 10 to the minus 30 newtons. So as long as any forces we're dealing with here are several orders of magnitude larger than 10 to the minus 30, which I don't think we'll have any problem with them being, we can get away with ignoring the effects of gravity because they're so small. So I have, in essence, one force on the moving electron from the magnetic field. And I'm going to apply Newton's second law. Newton's second law, recall, says if you add up all the forces on something, that's equal to the mass of the object times the object's acceleration. And there's only one force in this situation, but we have to remember something else from Physics 1, and that is when the acceleration corresponds with a direction change only, so the direction is continually changing, we call that kind of acceleration a centripetal acceleration, and we can calculate the size of that centripetal acceleration by taking the square of the speed divided by the radius of the circle. So that means if I put all of these things in, that the net force is only the force from the magnetic field, the mass is the mass of an electron, and the acceleration is the centripetal acceleration, which is the square of the speed divided by the radius. Well, the force on a moving charge depends on how fast that charge is moving and the magnetic field. So here's the new physics that we've introduced, that the force from a magnetic field is equal to the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between the velocity vector and the magnetic field vector. So we can plug that into the left-hand side of the equation. QVB sine theta equals the mass of the electron times v squared over r. We can solve now for the radius of the circle. So if we multiply both sides by r, we get r times q times v sine theta equals the mass of the electron times v squared. You can then divide by everything that's not r and put that in the denominator. The v in the denominator cancels one of the v's in the numerator, and we're left with mass of the electron times the speed of the electron divided by the charge of the electron times the magnetic field strength times the sine of the angle. Well, in this situation, the angle between the velocity vector and the magnetic field, which is directed into the page, is 90 degrees, and so I don't actually have to worry about the sine theta in here. It's going to equal 1. Alright, so then I'm plugging numbers in. The mass of an electron can be Googled, 9.11 times 10 to the minus 31 kilograms. The speed of the particles, we're told, is 6.27 times 10 to the 5th meters per second. The charge of an electron can also be Googled. That's 1.6 times 10 to the negative 19 coulombs. The strength of the magnetic field in this situation is 0.55 teslas. And the angle, again, is 90 degrees between the velocity vector and the magnetic field vector, so the sine of theta is 1. And if you crank all that out, and I did the calculation right, it turns out to be 6.49 times 10 to the minus 6 meters, or 6.49 micrometers. A couple more conceptual questions involving your observations from the lab. So we have a beam of charged particles that moves in a circle inside a uniform magnetic field. If we make the particles go faster, what does that do? Does that increase the radius of the circle, decrease the radius of the circle, or not change the radius of the circle? Correct answer is that it increases the radius of the circle. I don't know if you played around with this. The way that you do it in our experimental apparatus is you increase the plate voltage of the accelerating plates that form the electron beam in the first place. That ends up speeding the particles up more as they're shot through that essentially capacitor, and if they go faster, they will turn in a larger circle because the magnetic field is only applying a certain amount of force on them, and it's harder to turn something that is moving faster. A beam of charged particles moves in a circle within a uniform magnetic field. Increasing the strength of the magnetic field should do what? The correct answer here is that it decreases the radius of the circle. Experimentally, you see this by sending more current through these coils, and again, I'm hopeful that you experimented with that a bit in the lab. But if you make the magnetic field stronger, that makes the force that's applied to the moving charges also stronger, and that makes the radius of the circle that they turn within actually decrease. Finally, what happens if you increase the intensity of the beam and so there are more charges moving per time? Well, one of the ways you can increase the intensity of the beam in the system is to turn the filament hotter or a higher current through the filament so that there are more electrons boiling off. But it turns out this has no change on the radius of the circle, because if you have more charges moving per time, but you're not making each individual charge move any faster, then the force that's experienced by any individual charge stays the same, and the radius of the circle stays the same as well. Just a historical note, I'm not sure this is done much more, but when people were figuring out the physics of all of these small particles tens or hundreds of years ago, they often constructed bubble chambers, which would be a chamber that they would fill with a thin fluid that particles could move through, and you couldn't see the particles themselves, but as the particles moved in this fluid, they would create this trail of little tiny bubbles. And if you applied a magnetic field to this chamber, you could use the information that shows up in the tracks of these bubbles to figure out what kind of charge you had on the particles, and in fact also what kind of mass you had on the particles. So if you saw lines where the particles flew through the bubble chamber undeflected, that was evidence that the particles themselves did not contain a net electric charge. However, if you saw a place where you saw a particle turning in some sort of quasi-circular trajectory in this magnetic field, you could use that to figure out how much charge and how much mass those particles had. And friction in the system would actually cause them to spiral in. If there was no friction in the system, they should have continued in a circle of constant radius. All right, another example problem. At certain speeds, a particle moving through both an electric field and a magnetic field experiences a net force of 0. So again, let's think about this situation we had a few slides back. If I have a positive moving charge moving to the right and the magnetic field in this region points into the paper, that actually produces a magnetic force on the moving charge that is directed up. If I, however, put that magnetic field in the same place where I get an electric field, say from a parallel plate capacitor, and that electric field is directed downward so that it would push a positively charged particle downward, then it's possible that the magnetic force on the particle in the upward direction and the electric force on the particle in the downward direction would balance each other, and the net result would be that the particle would pass on through this system without its trajectory being affected in any way. In fact, if I could then tune the direction of the magnetic field and the direction of the electric field, I should actually be able to steer the particle either up or down in this particular system. And that's sort of the very basic physics behind how they made the early television sets. If you have a cathode ray television set at home, or have in your past, and you can tell because the back of the TV sticks out 2 or 3 feet behind the screen, it's actually firing charges in there at the screen and then using electric and magnetic fields to steer those charges so that they'll hit different little spots of colored phosphor on the screen and make the picture that you see. Alright, so what if we have charged particles that pass through what is known as a velocity selector with electric and magnetic fields at right angles to each other? A velocity selector is a device that will not have any net deflection on particles that are moving a certain speed, but if particles are moving slower or faster than that certain speed, they'll be steered up or down and ultimately removed from the beam of particles that you're trying to create. In this particular situation, the electric and magnetic fields are at right angles to each other. If the electric field has a magnitude of 450 newtons per coulomb, and the magnetic field has a magnitude of 12/100ths of a Tesla, how fast do the particles have to pass through this selector to not be deflected? So again, we've drawn vectors on a 3-dimensional axis to help us out here. The electric field is in the y direction, so a positive charge that's moving in the x direction would be pulled by an electric force in the y direction. But the magnetic field's in the z direction, and so a particle that's moving in the positive x direction, you can use your right-hand rule with a magnetic field that is in the positive z direction would experience a magnetic force that's in the negative y direction, and if those fields are just right in terms of balance relative to each other, this particle will pass through undeflected. So, what would the free body diagram on the particle look like? Well, and I certainly haven't tried to draw this in the same perspective as the coordinate system up here, but there should be a force on the charge from the magnetic field in one direction, and a force on the charge from the electric field in the opposite direction. And again, the undeflected is key here. We can use right-hand rule 1 to determine the force from the magnetic field is up in a given situation, and the force on a positive charge in an electric field is in the direction of the field, so say that's down in this situation. Again, this doesn't match the perspective of this 3-dimensional axis sketch up above. If we apply Newton's second law, that says the sum of the forces equals the mass times the acceleration. Well, if we have no deflection, we would like the acceleration to be 0. And what does that tell us? Well, it tells us that the two forces have to be equal to each other if there's no net deflection. So the force on the charge from the magnetic field equals the force on the charge from the electric field. We know how to calculate the force on the charge from an electric field. We've done that from our electrostatics work. The definition of an electric field was force per charge. So we've said force equals charge times the electric field. So the right-hand side of the equation becomes Q times E. The new stuff in this particular presentation is how to calculate a magnetic force, and that's the QVB sine theta. Well, the V and the B are at right angles to each other in this representation, so sine of 90 degrees is 1. And notice there's a Q on both sides of the equation, so I actually don't have to know how much charge I'm firing in here. If I double the charge, that doubles the size of the electric force, but it simultaneously doubles the size of the magnetic force, and so those two will still cancel each other. And so I'm left with a rather simple equation, at least in terms of terms in it. The speed times the strength of the magnetic field equals the strength of the electric field. And so you can solve that for speed. Speed is equal to the electric field divided by the magnetic field. That's 450 newtons per coulomb over 12/100ths of a Tesla, and that works out to be 3,750 meters per second. I could leave it as a Newton per Tesla coulomb, but you can trust me that you could actually, using the definitions, work that out to also be analogous to meters per second. So one last thing we want to touch on in this presentation, and that is that it's not very common for us to at least experiment with moving beams of particles. You did it in the lab once, and so we saw a electron beam moving in the E over M apparatus, and you steered that beam using electric and magnetic fields. But it is much more common for us to experience charge moving in conducting wires. And what happens in conducting wires? Well, we saw that charge moving in a magnetic field experiences a force. So the argument goes, a current, which after all is a collection of a bunch of moving charges, must behave the same way. It must feel a force in a magnetic field. So here's the form of the Lorentz force law that we have so far, F equals QVB sine theta. I'm going to do a little algebra here. I'm going to divide by delta t and multiply by delta t, which is the same as multiplying by 1, which is mathematically legal and allowed. But the reason I do that is, what is charge per time? That's our definition of current. And if I multiply the velocity of something times the amount of time it's moved for, that's a distance, or in this case it's going to be the length of a wire that something is moving through. And so we can write an analogous form of the Lorentz force law, which can be used to calculate the force on a wire that's carrying current. It would not be very common for me to know how much charge was moving in an actual current carrying wire, or how fast it's moving. But it is common to measure the amount of current that's flowing in that wire, and to be able to measure the length of that wire. And so this will allow us to calculate the force on a current carrying wire. Here's a picture to hopefully help illustrate what we're talking about. If I have a current that happens to be moving to the right in a piece of wire, and a magnetic field that is on or in that region that's oriented like this, I can use my same right-hand rule, point my fingers in the direction of the current, curl them into the direction of the magnetic field. My thumb is left pointing out of the page, so this current carrying wire should experience a force that is directed towards me or out of the page. And the magnitude of that force could be found using the equation in the box. Let's do one last sample problem in this section. If we have a triangular loop of wire, which is shown in the drawing, and it carries a current of 4.7 amps, and it's in a uniform magnetic field that is directed to the right, what's going to happen to it? What are the magnitude and direction of the magnetic forces that are exerted on each side of the triangle? And what is the magnitude of the net force exerted on the triangle? One comment, you couldn't just get a current of 4.7 amps to spontaneously flow around this wire. So you could imagine somewhere there are wires connected over to a power supply or what have you. But since we want to focus on the size of the forces on those current carrying wires, we're just going to imagine that all there is in this system are those current carrying wires. All right. So how do we do this? Well, we're first of all going to need to know the length of each side of that triangle. I know the length of the base of the triangle is 2 meters, and I know this is a 55-degree angle, so I use the cosine function, which relates the adjacent and the hypotenuse, to figure out that the hypotenuse must be about 3.5 meters long. And then I use the tangent function, which relates the adjacent and the opposite, to figure out that the opposite side of the triangle is 2.86 meters long. So I'm going to use those in my calculations here. Let's start with side AB and go in alphabetical order. The force on a current carrying wire is the magnitude of the current times the length of the wire times the magnitude of the magnetic field times the sine of the angle, and this is the angle between the current flow and the direction of the magnetic field in this particular situation. Well, the current is 4.7 amps. A to B has 2 meter wire. The magnetic field is 1.8 teslas, but the current is showing flowing to the left and the magnetic field is due right. The angle between those two directions is 180 degrees. The sine of 180 degrees is 0, so the force on the bottom part of that triangular loop is actually 0. If I go B to C, the current's still 4.7 amps. The length is what I deduced from my trig work over here, 3.49 meters. The magnetic field is a constant 1.8 teslas, and the angle between the direction the current is flowing and the direction of the magnetic field is 55 degrees here, so I plug in sine of 55 degrees, and I find a force of 24.2 newtons. I have to apply my right-hand rule and point my fingers along the direction of the current, curl them into the direction of the magnetic field. My thumb will be left pointing out of the screen, and so that is the direction of the magnetic field on the BC portion of the loop. Let's see, side AC is 2.86 meters long, same current, 4.7 amps, 1.8 Tesla magnetic field. The current's straight up, the magnetic field's straight to the right. That's an angle of 90 degrees, and the sine of 90 is 1. If you punch those numbers out, you'll find 24.2 newtons. And the direction of that force is into the page again, fingers on the right-hand rule pointing up, then curled to the right of the page in the direction of the magnetic field, leaves your thumb pointing into the screen, and that would be the direction. The magnitude is, of course, the same as it is on side BC. And so if you have one 24.2 newtons out of the page and the other is 24.2 newtons into the page, the net force then is in fact 0 on this loop. Doesn't mean the loop won't do anything, though. If you imagine holding this loop in your hands and pulling the right side of the loop out of the page and pushing the left side of the loop into the page, it would in fact spin. And so this loop, even though it has no net force on it, has a net torque on it. Torque, you'll recall from Physics 1, is the product of the force that's applied and something that's called the lever arm distance, basically how far you're applying that force on an object from an axis that that object is attempting to spin about. So, in certain situations, the forces applied to current carrying loops will produce a net torque, and you can work out how big that torque is. To calculate a torque, take the magnitude of the force you're applying, the magnitude of the lever arm distance, or the distance from the axis of rotation out to the place where you're applying that force, times the sine of the angle between that force vector and that distance vector, or displacement vector rather, and that will give you the torque. By the way, another way to write torque is to use a vector cross product like we've been doing for the Lorentz force equation. If you're familiar with that way, feel free to do that. So here's a little picture. If I have current moving in a loop of wire here as shown, on side 1 of that loop of the wire, the current's going to be moving up. Side 2, the current's going to be moving down. If I put that little loop of conducting wire into a uniform magnetic field between the ends of two magnetic poles, then there is going to be, and here we're switching to a top view diagram, the side 1 nearest to us, where current's coming towards us, is going to experience a force toward the top of the screen if you apply your right-hand rule. Side 2, where the current is going into the page in this perspective or down in this perspective, in a magnetic field directed to the right, we'll experience a force either towards us or toward the bottom of the page, depending on which perspective you're looking at here. And so these forces will act to spin this loop of wire in the magnetic field. And you've just made the basics of an electric motor when you do that. How much torque would there be on this situation? Well, the torque, you have to get the magnitude of the force. So that's the current times the length of the wire times the magnetic field. And in this orientation, the current and the magnetic field are 90 degrees away from each other, so I'm not worried about the angle part here. The distance from the axis to the place where the force is applied is half the width of the coil, so that's the W over 2 in this equation. And then phi here is labeled as the angle between the force vector and the displacement vector along the side of the loop here, and that's what you have to do in order to calculate how much torque you have in a given orientation. Well, that's just the torque on, say, side 1. The torque on side 2 is going to be identical because the force is going to be identical in size. W over 2 is still the distance from the center of that loop, and phi is still the angle between the displacement vector and the force vector. So if you put all those together, you get ILBW sine of phi, and let's see, length times width, if this loop is W wide and L tall, length times width is actually the area of the loop. So you can calculate how much torque you should get on a current carrying loop if you know how much current's flowing through that loop, how much area that loop contains, how strong the magnetic field is, and what the angle is between the loop and the direction of the magnetic field. If you have more than one turn, so if you have 5 coils, for example, but they're all oriented the same direction, the torque is just 5 times whatever a single loop would be, and so very often you'll see an N inserted in here, which is to indicate the number of loops in a particular situation. Now, this same coil, once it's turned to this orientation, will have maximum torque, because this is when the force is perpendicular to the direction of the lever arm. But once the coil is turned to this orientation, the force on one side is up, the force on the other side is down, and the net force there is 0, but so is the torque, because the force cannot act to spin this coil any longer. So I said previously, this is the basics of building an electric motor, and it is true, but you have to take a couple of other steps if you want to build an actual electric motor that will continue to operate for more than half a turn of the coil within the magnetic field. This concludes the lecture on magnets and magnetic fields for General Physics 2. As always, if you've spotted any errors in the presentation, I would appreciate you letting me know, and I hope this was a useful resource for you.